Good day, everyone. In this video, I will have a discussion about one of the topics in hydraulics, which is the relative equilibrium of fluids or liquids. Before we proceed, I would like to introduce myself. I'm Antonette Arpon, a third-year student from Bachelor of Science in Civil Engineering Section A at Eastern Visayas State University, Ormoc City Campus. Now that I have introduced myself, let's now proceed to the discussion. Our topic is relative equilibrium of liquids. Now let's know what this topic is all about. When we say relative equilibrium of liquid, it is a condition where the whole mass of liquid, including the vessel in which the liquid is contained, is moving at uniform accelerated motion with respect to the earth, but every particle of liquid have no relative motion between each other. This means that the mass of the liquid by means of a containing vessel is moving or travels at uniform constant acceleration. The treatment will center on a uniformly accelerated body of fluid wherein each particle is in equilibrium and at rest relative to every other particle in the liquid. Now, there are two cases of relative equilibrium. The first one is the rectilinear translation or the moving vessel, and the second one is rotation or the rotating vessel. But in this video, we will only be focusing solely on the rectilinear translation. As we recall the lessons we have learned in dynamics, the motion of a translating body moving in a straight line is called rectilinear translation. And one of the most common cases of straight line motion is that in which the acceleration is constant. And this is what we are dealing with, a body moving in a uniform constant acceleration. Now, a straight line could be horizontal, vertical, and oblique or inclined. An example of that would be a block moving horizontally, a block falling in a table, and a block sliding down in an inclined plane surface. But since this subject is hydraulics, the body that we are dealing with here is not a solid body, like this block, but a mass of water or of any liquid in a containing vessel or a tank. And that brings us to the three motions of rectilinear translation. However, in this video, I will only be including the horizontal motion and the vertical motion. First, let's talk about the horizontal motion. Assume that there's a rectangular tank at rest which contains a certain fluid, let's say water. Since the rectangular tank is at rest, the water surface is just laying flat horizontally. There is no angle formed in the water surface with respect to the horizontal. However, if the rectangular tank is moving with a constant horizontal acceleration, there is an inclination angle that will be created. As you can notice, the height of water in the front is lower than that of the rear part of the tank. It is because of what we call the reversed effective force. This reverse effective force, or denoted as REF, is always acting opposite to the direction of acceleration. Just like what we have here in the figure, if the acceleration is moving to the right, then the REF will act to the left, as if it pushes the water to the top of the rear part of the tank. Now, let's take a closer look to this new orientation of water surface. And let's zoom in, for example, a particle of water. The forces that are acting in this particle is its weight, denoted as W, and this weight is acting downward due to gravity. Then the reverse effective force, denoted as REF, which is acting opposite to the acceleration. This force tends to rise the water to such elevation. And lastly, the normal force, denoted as N, which is acting perpendicular to the water surface. And we all know that weight is equal to mass times gravity, or mg. The REF, or simply force, is equal to mass times acceleration, and the normal force stays as is. Since these three forces are concurrent forces, which means that they intersect at a common point, we can create a force polygon. By tangent function, we can compute the angle of inclination, or the angle with respect to the horizontal. So tangent theta is equal to opposite, the REF, over the adjacent, which is the weight. Substituting their formulas, REF is equal to mass times acceleration, and weight is equal to mass times gravitational acceleration. Canceling the mass, we now have this formula if the acceleration is horizontal. Next motion is the vertical motion. Let's consider a cylindrical tank with water at height h that is transported in an elevator at a constant vertical acceleration. In vertical motion, there are no changes in the orientation of the water surface, but there is a change in pressure at the bottom of the tank when it is moving in a constant vertical acceleration. In deriving the formula for the pressure at the bottom of the tank, let's consider the forces acting on the tank, which is the reverse effective force, the weight, and the force acting upward. By summation of vertical forces, we have force equal to weight plus REF. Now, by the unit pressure formula, force is equal to pressure times area, and weight in terms of the unit weight is equal to unit weight times volume plus REF, which is MA. Now, volume is just area times height, and mass in terms of density is equal to rho v, or density times volume. Multiplying this equation with 1 over area to cancel out area, or simply cancel out area since it is common on both sides of the equation, what's left is pressure is equal to unit weight times height plus unit weight over g times HA. We'll factor out common terms like the unit weight and height, where P is the pressure at the bottom of the tank, so this is now the formula for the pressure. Note that we will have to use the plus if the motion is upward and minus if the motion is downward. In addition, acceleration is positive A and deceleration is negative acceleration. Now that we know the formula, let's have some examples. For horizontal acceleration, we have first situation. An open rectangular tank filled with water is moving horizontally with acceleration of 2/5 of acceleration due to gravity. What is the angle of the water surface with the horizontal? What is the angle of the water surface with the vertical? What is the maximum horizontal acceleration can be imposed on a tank without spilling any water if the tank is 6 meters long, 2.4 meters wide, and 3.5 meters high with water to a depth of 3 meters. Given the problem, the horizontal acceleration, that's 2/5 of acceleration due to gravity, and acceleration due to gravity in SI unit is 9.81 meter per second squared. By simply substituting, we can now get the horizontal acceleration, which is 3.924 meter per second squared. Now we are tasked to find the angle of the water surface with respect to the horizontal, or let's denote it as theta sub h. And then the angle of the water surface with the vertical, let's denote it as theta sub v. And lastly, the maximum horizontal acceleration without spilling any water, or simply A. First, let's solve the angle of the water surface with the horizontal. So this is the initial orientation of the water surface when at rest. But when this open rectangular tank is moving horizontally with an acceleration of 3.924 meter per second squared, the water surface will look like this. Using the formula tangent theta is equal to A over G, substituting the given into this equation, we have tangent theta is equal to 3.924 meter per second squared over 9.81 meter per second squared. And by arctangent, we can compute for the angle. Arctangent 3.924 over 9.81 is equal to 21.80. So this is now the angle of the water surface with respect to the horizontal. Second, let's compute for the angle of the water surface with the vertical. By looking at this figure, we can simply get the angle with respect to the vertical by subtracting 90 degrees to the angle with the horizontal. So 90 degrees minus 21.80, we have 68.20 degrees. Lastly, we are to find the maximum horizontal acceleration without spilling any water in the tank. Given the dimensions of the tank, it is 6 meters long, 2.4 meters wide, which we can see since we are only seeing this in a side view position of our tank, and 3.5 meters high. with water at 3-meter depth. Now, what would be the maximum horizontal acceleration if there's no water being spilled in the tank? And with no water spilled means that one side of the water surface will be just at the tip of the tank, which will look like this. So using the formula tangent theta equal to A over G, and with tangent function, the opposite of the angle formed is 0.5 meters, since 3.5 minus 3 meters is 0.5. And it will always occur at the center of the water surface. What will add up here will be the same volume that was missing here. So if the tank is 6 meters long, then the adjacent over theta would be half of 6 meters, which means the adjacent would be 3 meters. By equating this and with the value 9.81 meter per second squared of our acceleration due to gravity, the maximum acceleration that can be imposed in the tank without spilling any water is 1.635 meter per second squared. And these are now the final answers in situation number 1. In our second example, we have an open rectangular tank, 3.5 meter high, 2.5 meter wide, and 6 meter long, is filled with water at a depth of 2.20 meters. What is the maximum horizontal acceleration can be imposed on a tank without spilling any water? If the tank accelerated to the left at 2.30 meter per second squared, determine the slope of the water surface. What is the angle of the water surface with the vertical? Given in the problem, the horizontal acceleration 2.30 meter per second squared and the dimensions of the tank. In the second example, we are tasked to find the maximum horizontal acceleration without spilling any water, then the slope of the water surface, and the angle of the water surface with the vertical. So this is just the same as to what we did in the previous example. Given the dimensions of the tank, it is 6 meters long, 3.8 meters height, 2.5 meters wide with a water to a depth of 2.20 meters. By using the formula tangent theta is equal to A over G and tangent function opposite over adjacent, we have 1.6 over 3. By equating the two equations, A over G is equal to 1.6 over 3, and with the value 9.81 meter per second squared of our acceleration due to gravity, the maximum acceleration that can be imposed in the tank without spilling any water is 5.232 meter per second squared. Second, we will compute the slope of water surface, or this is just simply the angle of the water surface with the horizontal. So by using the formula tangent theta is equal to A over G, and since given in the second problem the acceleration of the tank, which is 2.30 meter per second squared, let's use this into this equation. So arc tangent 2.30 over 9.81 is equal to 13.19 degrees. So this is now the slope of the water surface, or the angle of the water surface with the horizontal. Lastly, the angle of the water surface with the vertical. Same solution as to what we did earlier, 90 degrees minus the angle with the horizontal, 13.19, is equal to 76.81 degrees. And these are the final answers in situation number 2. So for vertical motion, we have the first situation. A bucket in an elevator contains 0.8 meters of water. Obtain the pressure at the bottom of the bucket when the elevator accelerates downward at 1.5 meter per second squared and when the elevator accelerates upward at 2 meter per second squared. Given in the problem, the height of water in a bucket, which is 0.8 meters, and we are to find the pressure at the bottom of the bucket when the elevator accelerates downward at 1.5 meter per second squared, and when the elevator accelerates upward at 2 meter per second squared. So let's solve the first problem by using the formula we derived earlier for the vertical motion, which is pressure is equal to unit weight times height times 1 plus minus A over G. But since the motion here is downward, we will use minus. So substituting the values into the equation, we have pressure is equal to 6.648 And the unit for pressure is kilonewton per square meter or kilopascal. And next, when the elevator accelerates upward at 2 meters per second squared. Same solution, but this time we will use plus sign since the motion is upward. Therefore, we have the pressure at the bottom of the tank, 9.448 kilopascal. And these are the final answers for our first problem. So let's have the second situation for the vertical motion. The problem states that if a container containing water 0.60 meter deep is carried inside an elevator that accelerates at 2 meters per second squared, evaluate the pressure in kilopascal exerted by the water at the base of the container if the elevator is traveling downward and if the elevator is decelerating upward. So given the height of water in a container, which is 0.60 meter, and given also is the acceleration of 2 meters per second squared, and we are tasked to find the pressure at the bottom of the container if the elevator is traveling downward and if the elevator is decelerating upward. By using the formula, pressure is equal to unit weight of water times height of water in the container times 1 minus A over G. We used minus here because it is traveling downward. So substituting the values into the equation, we have pressure is equal to 4.686 kilopascal. And next, the pressure at the bottom of the container if the elevator is decelerating upward. The same solution, but this time we will use plus sign since the motion is upward. However, we have to take note that the elevator is decelerating upward, which means that we have a negative acceleration here. Therefore, we have the pressure at the bottom is equal to 9.81 times 0.6 times 1 plus negative 2 over 9.81. So we have pressure is equal to 4.686 kilopascal also. And these are the final answers for this example. Now this is all for this video. I hope you have learned something. Thank you for watching.